I'm Mr. McBrien. This is TEJ3M, Capacitors, the exception to the rule. We've discussed a few times now the idea that electrons in a circuit don't accumulate. And remember, this was the basis of our conga line principle, where the current that goes into a resistor has to be the current that goes out of a resistor. The current that goes out of a battery is equal to the current that goes into a battery. Now, we have talked about that in terms of various components and said this is the rule of thumb in simple circuits. There is one kind of component that breaks this rule, and that is the capacitor. So today we're going to talk about capacitors and how they work differently than other components, how electrons essentially are stored up inside a capacitor, and this is done in a special way. So electric current is a flow of charge. A capacitor can store electric charge, therefore it can store electrical energy. Capacitors are used in various circuits, both with alternating current and with various ways of managing voltages. They're a key component in almost any electronic circuit as soon as we get to anything more complex than a simple light. So capacitors, in terms of a definition, they're two conducting surfaces, but they're separated by an insulating layer that we call a dielectric. Now, we don't need to, that's a very fancy word for just saying it's material that electrons cannot flow through. So a capacitor can just be a sandwich of, for example, aluminum foil separated by wax paper is an easy way to make a capacitor. Now, in terms of how they behave in a circuit, it's very interesting. We have a change in the way that circuits work. We now have circuits working differently as a function of time. So here's a simple circuit with a capacitor. Here, this is the symbol for a capacitor, a resistor, a switch, and a potential source. So a very simple circuit. Now, when we close our switch here, the potential gets, of course, applied across the capacitor through the resistor. And when this happens, the circuit behaves exactly like we'd expect. Current begins to flow. So electrons flow towards the positive end of the battery, and electrons flow away from the negative end of the battery. We've got a potential and we see a current. But remember, there's this dielectric material in the center of the capacitor that prevents current from going past. So what happens? This isn't exactly the same thing as a broken circuit or as a switch, and the reason is because these two plates are so close together. So what happens here? The charge begins to build up. So electrons accumulate on one plate of the capacitor, and a lack of electrons accumulates on the other plate of the capacitor. And this charge stores up. Now, we can quickly go through the math. I'm not going to ask you to reproduce this, but it's good for us to have a quick look at it. So the stored charge Q is proportional to the voltage. The more voltage, the more charge gets stored inside the capacitor. The other function of that, the capacitance, also decides how much charge can be placed inside the capacitor. So it's the combination of these two things, the voltage and the capacitance. The larger the capacitance, the more charge can be stored inside this device. Now, if we measure the charge in coulombs that we saw previously in our introduction to electricity, we measure the voltage in volts, then our capacitance is measured in what's called farads. So If we want to take an example, a quick example of storing charge this way, if we have a 10 microfarad capacitor and we put 10 volts across it, we can calculate how much charge will be stored inside it. So C equals Q over V. We can rearrange this to get Q equals CV. And then we simply get 10 to the negative 5 farads times 10 volts equals 100 microcoulombs. Like I said, I'm not going to ask you to reproduce those mathematics, but I did want you to have a look at it just to get an appreciation for it. Okay, now capacitors then block the flow of charge and accumulate charge when a direct potential is placed across them. However, something very strange happens when we put alternating current or an alternating voltage on a capacitor. So remember, AC swings between negative and positive as a function of time. Now in this case, we see something very funny, where a constant current can't flow through a capacitor. If the voltage varies quickly enough, an alternating voltage, it appears to be flowing through the capacitor because the capacitor charges and discharges, and it really doesn't interfere with the alternating current at all. And if we want to understand how this works, an easy way is to look at a single pane of glass and look at the way that sound can make it through that single pane of glass. When the sound from the lawnmower outside my office window hits the window, it hits it as a series of low pressure and high pressure forms as waves, longitudinal waves. Now what happens is, while wind can't blow through my window for the most part, the low pressure hits the window and the window bows out towards the outside. Then high pressure hits the window and the window bows towards the inside. And as it does this, it allows the wave to move, to propagate through the window itself. And much the same thing happens with alternating current in a capacitor. Now this is why you can hear sound outside an airtight window, and it's why alternating current appears to flow through a capacitor. Now, the charge buildup in the capacitor is, yes, a result of the voltage applied between the two plates. We understand that now. We've seen the mathematics of it. We can look at this and realize that initially, to build up that charge, we have to have current, and we've already seen that. However, as that current builds up, as that charge builds up, the electromotive force, the push against the current that we're observing, gets higher and higher as we store that charge. And if we want to think of it in terms of voltage, the opposing voltage gets higher and higher as the charge accumulates, and thus the applied voltage gets lower and lower, and the current gets lower and lower. And we can even look at a graph of this. When we apply the voltage across the capacitor, initially the current is very high. It's Ohm's law. However, the back voltage increases as the charge accumulates and the current drops away until the current eventually goes down to zero when the opposing voltage is equal to the original applied voltage. So I'd encourage you to give that a little bit of thought, because it's important to think about the way that a capacitor charges, because this is most of why it's useful in circuits and why we'll use it in our circuits looking forward. So let's design a circuit so that we can observe a capacitor in action. So this is a simple circuit with a 9-volt battery in this case, a polarized capacitor here attached to a resistor, and when we push down this push button here, it completes the circuit just as we saw previously, and it'll charge the capacitor. Since this push button is not pushed at this point, this is not involved in the circuit. Now, so what we can do is we can attach 2 ammeters here and observe this circuit in action. Okay, so let's have a look. So we press the first push button and the capacitor begins to charge, and we start with a high current defined by Ohm's law, and it drops away to 0. Then we can consider the second half of the circuit. We can release the push button from the charging circuit and look at a discharging circuit where our capacitor will be allowed to discharge back down to ground. So when we push the second push button, the charge that we accumulated in the capacitor will be allowed to flow through the 2 resistors and go down to ground. So let's observe that in action. So we press our second push button. Here, our current starts out high and begins to taper off as a function of time. So our capacitor is discharging until the current can no longer be observed. And if we wanted to, we could even have detached the battery from our circuit before discharging that capacitor. The capacitor contains everything we need to run our circuit. Okay, so we've seen capacitors in action, we've looked at the math, we briefly alluded to the symbols for a capacitor. The capacitor is a simple 2 lines in most cases, representing those 2 charging plates separated by a dielectric. Capacitors can be polarized, you can get variable capacitors, and there are several different ways of representing them. We will typically use this polarized capacitor look, or the one with the curved line on it, to represent that polarized capacitor. So what are our key points? A capacitor is 2 plates separated by a non-conductive material. The charge we can store in a capacitor is proportional to the voltage that's applied and its capacitance, measured in farads. A capacitor will block DC after the first initial current charges the capacitor, but it appears to allow alternating current to pass through it. And when we work with a capacitor, when we apply a potential across it, current will flow as the capacitor charges and then stop when the capacitor fills up. So that's our subject for today. Go ahead and have a look at the activity, building your own circuit for investigating the characteristics of capacitors. Have a wonderful night.